Hi, I welcome you all back to our course Digital Principles and System Design. Today we have started discussing about analog systems, digital systems, and what is the difference between analog system and digital systems, and then why do we need to study this Digital Principles and System Design course. And this course mainly deals only with the digital systems, right? And we have discussed about the difference between combination circuits and sequential circuits. Now we are going to discuss about the number systems. Number systems play a vital role in understanding the course Digital Principles and System Design. Okay, we have come across various types of number system, but we are going to discuss about the most commonly useful number systems in today's class. Okay, so number system, base are radix, and the symbols are digits of the respective number system. First, we should know what do you mean by base or radix. Base or radix of a given number system is one that uses or distinct symbols for or digits. Okay, so as I already told you that radix is represented by small r. Radix is represented by small r. So the base or radix of a number system R is one that uses or distinct symbols for or digits. For example, here the radix is 10 for decimal number system. So 10 distinct symbols, that is 0 to 9. Similarly, you can apply it for the other number systems. For binary number system, the base or radix is 2. So obviously 2 distinct symbols of binary number system is 0 and 1. For octal number system, the base or radix is 8. So 8 distinct symbols are used by the octal number system, that is 0 to 7. And finally, we are going to discuss about hexadecimal number system. Its base or radix is 16. So its 16 different symbols are 0 to 9 and A to F. The letters A to F represent the digits from 11 to 15 respectively. This is the only difference of hexadecimal number system compared to other number system, since this hexadecimal number system uses letters A to F for representing the digits 11 to 15 respectively. Okay, we know that decimal number systems are having much utility in our daily life. We know that. So that is the direct purpose of a decimal number system. Wherever we go, if you want to enter into ATM, if you want to get a cash, so what is that? You are getting a sum of 1000 rupees. Then 1000 is nothing but a number. Okay, it is a combination of digits 0 to 9, right? And if you are going for some shopping, so you'll be getting some kilos of vegetables or fruits. So 5 kg or 10 kg or 12 kg. So it's nothing but the combinations of 0 to 9. So why I am telling that means decimal number system is the system that we are using it in our daily life. Okay. Then we'll come to a binary number system. Binary number system is also very important, since this number system is used by the computers alone. Okay. Whatever we feed the information to the computers, computers can understand everything in terms of zeros and ones. So we should know the knowledge about binary number system for this reason. Okay. Then third one is an octal number system. Octal number system is going to use 8 different symbols range from 0 to 7, and hexadecimal number system is going to use 16 different digits or symbols. Okay. We'll know the purpose why we are going for hexadecimal digits and octal digits means. For example, if you want to write or if you want to program the particular microprocessor or microcontroller, you need to feed the data in terms of an hexadecimal digits. In those cases, the hexadecimal number system would be more useful. So I repeat, for programming the microprocessors, you need to feed the data in the form of an hexadecimal values. In those situations, the hexadecimal number system would be more useful. And one more application is, for example, you have given a 64-bit data. Okay, 64 bit in sense bit refers to an values of binary number systems. I can say that binary number system symbols are considered as a binary digit. That binary digit is simply abbreviated as a bit. Okay, so if whenever we are using a term called as a bit, it always refers to the binary number. So 64 bit means, what is the meaning? So we are going to have 64 different binary digits in terms of zeros and ones. Is it possible to remember that value? Obviously not. Okay, in those cases we can represent those 64 bits in terms of 16 hexadecimal digits, which means each hexadecimal digit can be used to represent 4 bits each. Okay, that is the meaning of an hexadecimal value, or that is the application of an hexadecimal number system. That is, you can represent an equivalent binary value through hexadecimal value. So it is very difficult to remember an 64 bit long of information in terms of zeros and ones. Rather, you can convert those 64 bit information into hexadecimal value, which reduces the size by 1/4. That's what I told. 64 bit value means we can get 16 hexadecimal digit. So clearly it reduces the 64 bit size to 1/4 of hexadecimal digit, that is 16 hexadecimal digit. Okay. Similarly, you can use the octal number system for representing the binary number system. In contrast to hexadecimal, how octal number system will reduce means it will reduce 1/3 length of the binary number system. Okay, for example, if you want to represent 27 bit binary number in octal means there would be a maximum, there would be exactly 9 octal digits needed. Okay, so each octal digit will take or will be useful for representing group of 3 bits. Okay, so both octal and hexadecimal codes can be useful for representing the binary values in the simpler fashion. That is the purpose of using octal and hexadecimal number system. Okay, now we will discuss about the conversion. Conversion can be categorized in 4 ways. One is decimal number system to other number systems. Second one is other number systems to decimal, right? Third one is binary to octal and vice versa. Binary to hexadecimal and vice versa. Yeah, okay. So the conversion can be done from one number system to another number system. That can be categorized in these following 4 ways. First one is converting the values from decimal number system to other number system. Then second category is converting the values from other number systems back to decimal number system. Okay. Third one is converting a binary value directly to an octal and vice versa. Vice versa means converting octal to binary. And fourth one is converting binary value to hexadecimal and vice versa, that is hexadecimal to binary. Okay. These are all the four different ways of converting the values from one number system to another number system. As far as today's session concerned, now we'll see the first part, that is called as a decimal number system to other number system. Okay. Decimal to other number system. Okay. So there is a common procedure for this conversion. If you are trying to convert a given decimal number to any other number system, what is the procedure is, you have to split a given number into two parts. That is integer part and fractional part, and you need to apply a separate procedure for each. Then you have to combine the result. Now I will tell you the procedure for converting the integer part into other number system. Okay. So what is the procedure? You need to divide a given integer part by the base or radix to which our decimal it has to be converted. Okay. Is it clear? I will repeat once again. If the integer part of the decimal number has to be converted to any other number system, what you need to do is, you have to divide by the base to which the number has to be converted. Okay. Right? For a fractional part, you need to multiply by the base to which the number has to be converted. Okay. Now we'll go through by an example so that you can understand in a better. We'll go through by an example so that we can understand in a better way. 59.125 base 10 we are going to convert to binary. Okay, so what is the procedure is, we need to apply the procedure for integer part separately and fractional part separately. Okay, now we'll do it with integer part. For integer part, what we need to do? We need to divide by the base to which the given number has to be converted. Now we are going to convert this number to binary, so we need to divide this integer part by 2. Okay, 29 2s are 58, remainder 1. 14 2s are 28, remainder 1. 7 2s are 14, remainder 0. 3 2s are 6, remainder 1. 1 2s are 2, remainder 1. So further we cannot proceed with the division since we have got the quotient as 1 there. Okay. Right. So now we need to write the values in this order. So the binary equivalent of 59 is 111 0 11. Is it clear? Now we'll do for the fractional part. Fractional part, what we need to do? We need to multiply the fractional part by the corresponding base or radix to which our given number has to be converted. Here we are converting to binary, so we need to multiply the fractional part by 2 until we get a whole number. Okay. So 0.125 into 2 equal to 0.250. So we are looking at the result. It is not giving a whole number. So we need to repeat the process. That is, we need to take only the fractional part out of it. Okay. Right. So fractional part is 0.250. 0.250 into 2. So what is that? 0.5. Then still we didn't get a whole number. We need to repeat the process. 0.5 into 2, which is nothing but 1.0. So now we got an integer part, that is nothing but a whole number. So this is the point we need to stop the process. Okay. Now we need to write the values in this order while we are writing it for fractional part. So what is the fractional part value? 0, 0, 1. Okay, and put the suffix as the corresponding base. So this is a binary number, so we have used the base or radix under the suffix. Okay, this is how we need to do it for the other number system. Okay, while we are converting your decimal. Okay, now we'll see the other number systems. Now we'll take the same example. We'll try to convert to octal. Okay. So what is the same procedure? So here what we need to do? We need to divide the integer part by 8 and multiply the fractional part by 8. Okay. So 59. How many times? 7 8s are 56. Remainder is 3. So we need to start with this because 7 is lesser than 8. Okay. So the integer part is 73. Now for fractional part we need to multiply by 8. 0.125 into 8 is nothing but 1.0. So we have got the whole number in the first step itself. Okay. So the result would be 73.1 base 8. Okay. We'll repeat with the hexadecimal number. Okay. So what we need to do? The same rule. We need to divide the integer part by the base to which the given number has to be converted. Here we are trying to convert to hexadecimal. So we have to divide the integer part by 16. How many times 16 here? 3 16s are 48. Okay. Remainder 11. So now I am going to write it as 3b. It is important to note that here the remainder we have got is 11. Now we are trying to represent the value in hexadecimal. In hexadecimal 11 is nothing but letter B. Okay, that is why 3B. Okay, dot. We need to multiply 0.125 into 16. 0.125 16 is nothing but 2.0. The rule is very same. You have to go on multiplying the fractional part until you get a whole number. We have got it in the very first step in both octal and hexadecimal cases. Okay, so the result would be 3b.2 base 16. Okay, this is how you need to convert the given decimal number to other number systems. Okay, now we'll see the second category of an conversion, right? Other number systems to decimal. Here the procedure is very common. That is, you need to multiply each digit of a particular number by integral power of its own base. Then we need to form the corresponding sum that will give the desired result. For example, if you are trying to convert binary number to decimal number, then what we need to do? We need to multiply each binary digit or bit by integral power of 2. Then forming the sum will give the value in the decimal number. Similarly, if you want to convert a given octal number to decimal number, then what we need to do? We need to multiply each octal digit by integral power of 8 and then we need to form the sum. That sum will give the desired result in decimal number, and it is very same for an hexadecimal number. Okay, now we'll see an example for each conversion. Okay, first we'll try to convert .101 base 2, right? Okay. So as I already told you, if you want to convert to decimal, you have to write, you are trying to convert this number to decimal. So as I already told you, we have to multiply each binary digit by integral power of 2 in case of a binary number, and if it is in case of an octal digit, we need to multiply each octal digit by integral power of 8 and so on. Okay. So here it is a whole number. So this is an integer part. We know the place values, right? So it could be this part could be 2 power 0, 1 into 2 power 0, 0 into 2 power 1, 1 into 2 square, 0 into 2 cube, 1 into 2 power 4. Okay. Based on which only we need to find the place value for the fractional part. This is 2 power 0, that is 1's place. So here what it is, it will come 2 power minus 1, 1 into 2 power minus 1, 0 into 2 power minus 2, 1 into 2 power minus 3. Okay, this is how we are going to do it. Okay, now we'll see. This is 1 into 2 power minus 3, which is nothing but 1 by 8.125, and then 0 into 2 power minus 2, 0 into anything is 0, okay, 0 into anything is 0, then 1 into 2 power minus 1, which is nothing but 1 by 2 equal to 0.5. Okay, 0.5. You can use this value otherwise in order to avoid the confusion. Okay, 0.5. From here, 1 into 2 power 0, we know that anything power 0 is 1. Okay, then it is 1. Then 0 into 2 power 0 is 0. Then 1 into, it's 0 into 2 power 1, not is 2 power 0, 0 into 2 power 1, there is 1 into 2 square, that is 4, then 0 into 2 cube is nothing but 0, then 1 into 2 power 4, which is nothing but 16. Okay, what is the total? What is the total we will be getting? This is 5, right? 52625. Okay, then in fractional part we are getting 625. In the integer part we will be getting 21. So what is the answer is 21.625 base 10. This is how you have to do. Is it clear? We need to multiply each binary digit in case of a binary number by integral power of 2. We need to multiply each octal digit by integral power of 8. Okay, and we need to multiply each digit by 16 in case of an hexadecimal number, and then we need to form the sum that will give the desired result in the respective decimal number. Okay, is it clear? Once again I will repeat it. This is 1 into 2 power minus 3 is nothing but 1 by 8, that is equal to 0.125. 0 into 2 power minus 2, 0 into anything is 0, and 1 into 2 power minus 2 is nothing but 1 by 2, that is equal to 0.5. then 1 into 2 power 0, anything power 0 is 1, so 1 into 1 is 1, then 0 into 2 power 1 is 0, and 1 into 2 square is 4, and then 0 into 2 cube is 0, 1 into 2 power 4 is 16. So if you add both integer and the fractional part, we will be getting the result as 21.625 base 10. Okay. We'll go by another example. Convert 765, simply we'll take for better understanding, base 8 to decimal. Okay. So as I already told you, the procedure is very same. So what we need to do? You have to take 765 and each digit must be multiplied by integral power of 8 here. Okay. So 5 into 8 power 0. Anything power 0 is 1. So 5 into 1 is 5. 6 into 8 power 1, which is nothing but 8 power 1 is 8. So 6 into 8 is 48. And then 7 into 8 square, which is nothing but 7 into 64. What is 7 into 64? 4 sevens are 28. 64, right? 4 sevens are 28. 8, right? So 42. 448. Yes, exactly. 448. So what you will be getting by adding this sum? 13, 21, 2, 6, 10, 5. So the result would be our 501 base 10. Remember, you should not forget to represent the corresponding base or radix of a number system. Is it clear? Yeah? We will go for the example of converting an hexadecimal to decimal number. Now we will take an hexadecimal number, convert 7 AC base 16. Okay. So how we are going to do? We are going to multiply each hexadecimal digit by integral power of 16. Okay. C into 16 power 0, which is nothing but C, because anything power 0 is 1. So C, so while we are converting to decimal, what is the value of C? What is the value of C? It is 12. Okay, it is 12. Then A into 16 power 1. A is nothing but, while we are converting to decimal, A becomes 10. So 10 into 16, which is nothing but 160. Correct? Then 7 into 16 square. 16 square is nothing but what? Can anyone tell me that? It is 256. So 256 into 7, what will be getting? 42, 9, 17. Right? 6 sevens are 42, 4, 5 sevens are 35, 39, 9, 2 sevens are 14, 7. Yes. It is 1792. Okay, we have to add this. 4, 7, 16. 4, 7, 16. Yeah. 2, 9, and then 1. Is it clear? 2 plus 2, 4. 7 plus 9, 16. So carry 1, 2, 9. Right. So the answer would be 1964 base 16. Right? I think we'll stop this session with this. The rest of the two categories of conversion, we'll discuss it in the next class.